Welcome students, welcome to expert tutorial. So today we'll discuss about a new chapter, that is elasticity. So the first question arises, what is elasticity? So see the picture. I am trying to stretching a rubber. So when a rubber is stretched, its length is increased, but if the stretching force is withdrawn, it returns to its original length. So when we apply an external force upon a body, then there is a change either in size or shape or both of the body. And this force is called the deforming force. So this is the deforming force. And due to the stretching force, according to Newton's third law, there develops a force of reaction inside the material of the body. So this is the force of reaction and this is the applied external force. So due to this external force, a reaction force has arisen inside the body, and this force is equal to this applied force in most of the cases. And this force of reaction helps the body to regain its original shape and size when the deforming force is withdrawn. So this is a general property of the material, and basically it arises due to the intermolecular forces. Basically the molecules try to be at its own position, and it is a general property of the material of the body. And this property of the solid materials to return to its original shape and size after the removal of the deforming force is known as the elasticity. And the force which produces a change in the configuration of the object on applying it is known as the deforming force. See here, this is the deforming force I have applied. Basically I have applied a weight in this direction. So this is basically the deforming force, and due to the application of this deforming force, another force arises. Another force arises, and this is the reaction force. Basically this particular force is known as the restoring force. I'm coming to this later. Now if you can see the picture, this spring, I am trying to stretch the spring. So when I am applying a force, it is stretched, but there is a certain limit. That particular limit is known as the elastic limit. So elastic limit is the upper limit of deforming force up to which, if the deforming force is removed, the body regain its original form completely. So elastic limit is that particular limit up to which I am applying the force. When I remove the force, the body regains its original form completely. And beyond this, if the deforming force is increased, the body loses its property of elasticity and get permanently deformed. This is known as the elastic limit. I'll make a lot of discussion in another video about this elastic limit. Okay. Now coming to the stress. See here. See in this picture, I am applying a force here in this direction. I am applying a force so that it is stretched, it is elongated. But after the application of force, it will regain its original shape. Why? Basically, whenever I am applying a force, another force developed in this direction, just in the opposite direction, due to the Newton's third law. This particular force is known as the restoring force. So this is the restoring force. And what will be the definition of the stress? So the stress is nothing but the restoring force per unit area. This is the ratio of restoring force per unit area. But which area? I will take. Basically, this area is the cross-sectional area. This is the cross-sectional area. So I have applied a force on this cross-sectional area. I'm pulling this body along this cross-sectional area. So there develops another force in the opposite direction. This is known as the restoring force. So I have to calculate this restoring force per unit area, and it will be the stress. So in most of the cases, this restoring force is equal to the deforming force. Okay. Now since it is the force per unit area, so its unit will become Newton per meter square, and its dimensional formula is ml minus 1 t minus 2. Now coming to the strain. So strain is the fractional change in the configuration. So what is this fractional change in configuration? Basically, the fractional change in configuration is if we try to pull this, like this picture, I am trying to pull this one, so it is elongated. So elongated means it has increased in its length. So the change in the length to the original length is also a strain, is also a fractional change in the configuration. In the configuration, that is in the length, the fractional change in the length, so it will be also strain. Now strain is change in configuration to the original configuration, since it is the ratio of the same type of that is the ratio of the configuration, so it has no unit, and it is also a dimensionless quantity. So it is a very vital property, that is the strain has no unit and it is a dimensionless quantity. So if the question arises, tell a name of the dimensional, tell any name of the dimensionless quantity, so just the answer is strain is the dimensionless quantity and it has no unit. Okay, now there are three type of strains. One is longitudinal strain. So what is this? Just see this picture. I am pulling this uh, rod or something else. I'm trying to pulling this, so it will be elongated. Next picture, I'm pushing this. Okay, so basically in the first picture I am pulling this, and in the second picture I am trying to compress this. So what will happen? In the first picture it will be elongated, and in the second picture it will be compressed. So see here, in the first picture it is elongated to delta L, and in the second picture it is compressed to delta L. So the longitudinal strain is basically tensile stress is also called longitudinal stress and strain, and compressive strain is also called the longitudinal strain. So longitudinal strain is the change in length by original length, or the ratio of the change in length to the original length. So here this longitudinal strain in both the cases, that is in first case and the second case, it will become delta L, that is change in length by original length. Okay, and since it is the basically it is the ratio of length, so it has no unit. Now coming to the volume strain. So volume strain, see the picture. Basically I have applied a force to this cube. Okay, so due to the application of external forces, if an elastic body changes its volume without changing its shape, the strain is called the volume strain. So volume strain is change in volume to the original volume. You can feel the pressure when just a body is immersed inside some liquid. You will feel that it will the liquid is trying to compress the body. So there will be a volume strain. There may be a volume strain when you immerse a body inside the liquid. Okay, So the volume strain is the change in volume to the original volume. So a volume strain, suppose its original volume was V and the change is, sorry, its original volume was V1 and the changed volume is V2. So change in volume is V1 minus V2 and original volume is V1. So this will be the volume strain. Now coming to the shearing strain. So shearing strain, suppose I am applying a force from the sideways like this. So what will happen? Just like this. Please check the picture once again. Okay. So now it was its initial stage. So no force is applied over here. And this is the second case when a shearing stress is applied. So this shearing stress is applied sidewise. So this is sidewise force. And it is defined as the ratio of the displacement of a layer to its distance from the fixed layer. So this layer is displaced to this x and the distance from its fixed layer. So shearing strain will become this x by this length is h as shown in the picture. So x by h. So this is basically, what is this x by h? If this angle is theta, so it will become, this is basically perpendicular by base. So this is tan theta. And if the theta is very small, I'm not applying a large force. So if this theta is very small, tan theta becomes, so theta, if theta is small, so tan theta and both the sine theta is equals to theta. So this x by h becomes theta, and this is the shearing strain. This is the shearing strain. Okay. And now coming to the lateral strain. So lateral strain is that when a wire is stretched along its length, see this picture, I am stretching this along its length, so it elongates. Okay, it is elongated. You can see the picture, it is elongated. It's suppose its original length was L. So after application of the force, this is the change in the length, this is delta L. So it is elongated to delta L. Okay. So when a wire is stretched along its length, it elongates, but at the same time it gets thinner also. So it gets thinner also. Okay. That is, laterally it gets deformed. So the lateral strain basically arises due to the change in the diameter. Okay. So the ratio of the change in the diameter to the original diameter is known as the lateral strain. Suppose its original diameter was d1, it was its original diameter, and after the application its diameter becomes d2. So the change in the diameter to the original diameter, that is lateral strain. So lateral strain equals to change in the diameter, that is d1 minus d2 by d1 original diameter. So this is the lateral strain. Okay. Now there is another important thing that is known as the Poisson's ratio. So Poisson's ratio is nothing but the ratio of lateral strain to the longitudinal strain. So if the lateral strain means this change in the diameter to the original diameter. So if the change in the diameter is delta d and original diameter is delta d, so the lateral strain is delta d by d, and this longitudinal strain is the change in the length to the original length, that is if the change in the length is delta L and original length is L, So Poisson's ratio sigma equals to delta D by D by delta L by L. Okay. So, and also uh, there are some important points, that is its value. Okay. The theoretical value of the Poisson's ratio lies between -1 and 0.5, that is half, but its practical value lies between 0 and 0.5. Okay, so please note down all the things I am discussing over here. All the things are very important for your exam. So please take a note all of this. Now coming to the Hooke's law, very vital. So Hooke's law is states basically within the elastic limit the stress is proportional to the strain, so that you can write that stress by strain equals to constant. But within the limit, this is very important. Within the limit, suppose you are trying to elongate, or you are trying to pull uh, a rod, so that what will happen, it will be elongated. You have increased the force further, so what will happen, it will further be elongated, but it has a limit. After the limit, it will be broken. Okay, so within the limit of the elasticity, the stress is proportional to the strain, and this constant, stress by strain, is constant. This constant is known as the modulus of elasticity or the coefficient of elasticity. And since this is the ratio of the stress by strain, so since strain has no unit, so this constant, that is the modulus of elasticity, has the same physical unit as stress. Okay, now there are several types of this modulus of elasticity. That first one is Young's modulus of elasticity. So please see this picture. This is a rod of length L, and I have applied a force in this direction, that is F, and after the application of this force, it is elongated to this delta L amount. So the Young's modulus, the definition is the ratio of normal stress to the longitudinal strain. This is basically the definition of the Young's modulus, that is Young's modulus equals to normal stress by longitudinal strain. So y, you can see, we can write from this picture, this y equals to normal stress. What is stress? Stress is the force per unit area. And one thing, that is this force is calculated across this cross sectional area. So this is the cross sectional area, and this force per unit area is basically the force per cross sectional area. So Young's modulus will become force per unit area, unit cross sectional area, divided by longitudinal strain. What is this longitudinal strain? Is the change in the length, that is delta L, to the original length, that is L. So delta L divided by L. So this is the Young's modulus of elasticity, and its unit is Newton per meter square, as the strain has no unit. So it has no unit, that's why its unit is the Newton per meter square, that is the same as the unit of stress. Bulk modulus of elasticity. So bulk modulus arises due to the application of the volume stress. So the ratio of the volume stress and the volume strain is known as the bulk modulus. See here, I have applied a force from all the directions here, so that its volume decreases to delta V. So the ratio of the normal stress to the volume strain is known as the bulk modulus. So the bulk modulus equals to bulk modulus. Okay, so this bulk modulus equals to normal stress. Normal stress is force per unit area, and volume strain. that is its volume changes to delta V by V, original volume. And you may write this, that is force per unit area is nothing but the pressure, this pressure. So this is basically pressure by volume strain. So this is the bulk modulus, and in most of the cases it is a negative, because in most of the cases after application of the force volume is decreased. Okay, now coming to the modulus of rigidity or rigidity modulus. So it is the ratio of the shearing stress and shearing strain. So eta, it is known as eta, is basically tangential stress divided by shearing strain. So it is the ratio of shearing strain, shearing stress and shearing strain. Okay, and its unit is also Newton per meter square. Now a very important question, which is more elastic, rubber or steel? Now this question is very difficult to answer, as the definition of elasticity tells us that it is the property of the material uh, due to which the material tries to regain its original shape after the deforming force is withdrawn. So in our from our general idea, we can see that after application of the force, the rubber basically regain its original shape. So in from our daily life, we from our daily life we can say that rubber is more elastic, it seems to us, but the answer is no. Steel is basically more elastic than rubber. Why? There is another definition of the elasticity, that is whenever you are applying a force on a body, it opposes the change in its shape or size. So this opposing force is too much higher in case of a steel. That is, you cannot deform the steel by applying a small force, but you can deform a that suppose you can elongate a rubber by applying a very small force, but you cannot elongate a steel by applying that same amount of force. That's why the steel is more elastic than rubber, because uh, a body is said to be more elastic depending on how fast it gains its original shape after removal of external force, that is known as the deforming force. So when a force is applied to steel, it is deformed, but it immediately regains its original shape within a fraction of seconds, which is not in case of rubber. And also the steel, you have to apply more force on a steel for such a deformation, or you have to apply more force in case of a steel for to elongate the steel. And that's why you can say the rubber band is not really very elastic, it is just a stretchable thing. Okay, so this question is very important, and after this I'll make another video discussing the stress strain graph. So thank you very much.